Every time you reach out to touch a stainless steel appliance, your hand is inches away from raw, high-voltage energy. A highly engineered, invisible shield keeps that energy contained and away from your fingertips. To keep us safe, the electrical grid relies on a universal reference point of exactly 0 volts, mean the exact same thing. They don't. It all comes down to a single physical rule. Electricity only moves when there is a difference in pressure, what engineers call electrical potential. Energy always rushes from a zone of high pressure to a zone of lower pressure. If a system fails to manage these pressure differences and you touch the wrong metal surface, your body bridges that gap, becoming the grid's path of least resistance. The first layer of defense is bonding. Its sole purpose is to connect metal parts together to equalize local potential. In this photo, a green and yellow wire physically bridges the metal plumbing, forcing both pipes to share the exact same electrical pressure. If there's no difference in voltage between them, current cannot flow. The second layer is earthing. Looking inside this electrical panel, we see heavy copper bus bars and green and yellow cables routing down to an earth point. Earthing takes those bonded metal parts and physically connects them to the dirt outside, anchoring them to a true 0-volt potential. If insulation degrades inside a washing machine and a live wire touches the outer casing, it instantly becomes a high-pressure zone of dangerous potential. Because it's earthed, current bypasses the human entirely, rockets down the safety wire, and forces the circuit breaker to trip. Bonding and earthing do not stop a fault from happening. They deliberately redirect it, killing the circuit before it can kill a person. Moving back up the line to the power source, we encounter grounding. Unlike earthing, which deals with dead metal, grounding connects the live, current-carrying neutral wire to the earth, stabilizing phase voltages across the entire network. When this critical neutral connection snaps or heavily corrodes at the transformer, the entire system loses its 0-volt anchor. This triggers a disaster scenario known as a floating neutral. Without a fixed earth connection, the neutral point breaks free and drifts erratically towards whichever phase pulls the heaviest load. Entering a home, this drift causes voltage on some pathways to plummet to 110 volts, while others catastrophically spike to 340 volts. Grounding acts as the vital anchor that keeps alternating phases balanced, preventing the grid from tearing itself apart from the inside. At the macro scale of high-voltage infrastructure, managing these potentials requires complex engineering. This schematic of a substation shows transformer windings, a grounding bank, and a protective relay architecture, all designed to manage massive fault energies. When immense power lines fault, a staggering amount of current is dumped directly into the earth. But dirt naturally resists electrical flow, preventing it from absorbing all that energy instantly. This creates ground potential rise. Voltage pools at the injection point and ripples outward, forming concentric rings of decreasing electrical pressure. Standing with feet in 2 different voltage rings creates a pressure difference that drives a lethal current up one leg and down the other. In a high-voltage fault, you don't even have to touch a wire to be electrocuted. The dirt itself becomes a lethal gradient of potential. Bringing this back down to the residential scale reveals how confusing these precise engineering terms leads to illegal, deadly wiring practices. A common shortcut occurs when an installer decides to use the safety earth wire as the neutral return path to power a device. This forces everyday operating current through the green earthing wire, but that protective path is physically thinner and has a naturally higher resistance. This creates a continuous voltage drop, actively energizing the outer metal casings of the washing machine, refrigerator, and oven. By forcing a protective path to act as a return path, a system explicitly built to save lives is transformed into an active shock hazard. Grounding and earthing are highly calculated pathways designed to maintain absolute balance. They dictate the flow of faults, keeping the modern world safe to touch.